When you think about bacteria, what's the first image that pops into your head?
Maybe this? Well, maybe not.
For decades, the fluid mosaic model suggested that bacterial members were simple, homogeneous bilayers where proteins diffuse freely.
Under this view, bacteria were considered structurally basic cells. However, recent evidence challenges this, showing that bacterial cells are far more complex, possessing functional membrane microdomains, FMMs, non-skilled platforms that organize specific lipids and proteins to regulate cellular life. This discovery represents a fundamental shift in microbiology.
FMM are the prokaryotic counterparts to eukaryotic lipid routes.
While eukaryotes rely on cholesterol, bacteria use rigid lipids like halpanoids and polyisoprenoids to create disordered regions. The structural stability of these domains depends on flow-twin proteins, specifically Flow A and Flow T, which act like scaffolds to recruit beta protein partners.
The most significant findings is that FMM act as ligation platforms. They concentrate specific cargoes like sensor kinases for biofilm formation,
The SEC machinery for protein secretion, and FTSH proteases to increase the efficiency of biochemical reactions. Crucially, these domains prevent non-specific aggregation, ensuring proteins assemble into productive functional complexes. This organization is vital for survival and virulence. In pathogens like Campylobacter jejuni, disrupting flocculing impairs the ability to invade host cells. In Mycobacterium and tuberculosis, FMM proteins are concentrated in extracellular vesicles, offering a new marker for immunodiagnosis. Future research must now focus on the precise molecular mechanism of lipid specificity and how these domains change over time. Overall, the discovery of functional membrane microdomains fundamentally revises our perception of bacterial membranes from simple bilayers to dynamic heterogeneous factories. However, as it is an emerging field, several outstanding questions still remain for future research. First, what are the precise molecular mechanisms that govern lipid specificity and the initial formation of these domains? Second, how do these domains change temporally during different stages of the bacterial's life cycle, or under environmental stress? And finally, can we exploit the concentration of MMM proteins in extracellular vesicles, specifically in M. tuberculosis, to develop more accurate immunodiagnostic tools? The insights I've shared today are based on the article Exploring Functional Membrane Microdomains in Bacteria, an Overview, by Daniel Lopez and Gudrun Koch, published in Current Opinion in Microbiology. Thanks for watching.